Kavita, shall we start?
Yes, sir. Yeah, hi all. A very good evening and a warm welcome for ANSET's series of webinar on SDV. This is session 2 on the role of HPCs in SDV. Let me share my screen. Okay, I hope it is visible. So I'll just take the first couple of minutes to quickly recap the goal of SDV, and we have majorly seen the three pillars of SDV. The one is the SOA architecture, that is the service oriented architecture, and the second thing was the high performance computer and the artificial intelligence inculcated in it, and the third was the vehicle operating system. So these are the three pillars that we were discussing during the last webinar. And today we are going to focus majorly on the role of high performance computers, abbreviated as HPCs, for the implementation of software defined vehicle. And as I said, this is just a fast recap. We have the four major innovations happening in our industry, and the hybrid combination of automation, that is autonomous driving, and the connected mobility has enhanced its wing with a new revolution called the software defined vehicle. So this is just to define you that in the traditional vehicles which we have currently on roads, that too mainly on Indian roads, we have the controls lying with the hardware mostly. And this term, the software defined vehicle, it is going to take the functionality and controls towards the software. So software will be the major component that drives the functionality, control, as well as the user experience. So when we talk about the user experience, the customers nowadays are expecting that the vehicles which they spend lakhs and lakhs should be giving the experience similar to their smartphones. And the market players like Tesla, Neo, Lucid, they have already launched their self-driving cars in some few parts of the country, and this further stimulates the interest among the customers, and they show their disinterest towards the current vehicle models where they are unable to do any upgradation or feature updates. So this is the base stimuli for the SDV to boom up in the coming decades. And we cannot directly consider a smartphone on wheels because it has so many drawbacks. It is going to consider the lives of so many inside the vehicle as well as on the road. So it is rephrased like habitat on wheels, meaning we have to keep up the physical features of the vehicle which is currently being delivered. To that we have to add the customer experience, that is the user experience, which is available in the smartphones as well. So we are about to combine two different things which don't meet at all. So this is the challenge that we are facing. So the clash between the two different dimensions, meeting out the physical experience, we go with the V model for developing the softwares, and we have to stick to the functional safety standards. We have to see the accelerators of the systems and so many things like wise. Whereas when we wanted to give digital user experience, we have to keep up the agile methodology, which are two different paradigms, and the challenge is to make them occur in a single system. And so for this to be achieved, we go with the digital first approach, meaning to give the user experience considering that the vehicle features are retained. To get the digital experience, the new features that the OEM or the third parties who are trying to launch it, they will first develop and test it in a virtual cloud environment, get the early user feedback before going for production. Once the feedback is satisfactory, they will start producing it and then go for continuous improvement. And this is the thing planned in the future, okay, in the digital first approach. So, as we saw, to obtain all these things, we have to focus on the three major pillars: the SOA architecture, the HPC's role in implementing it, and as well the contribution of artificial intelligence to the autonomous driving. And we have to consider the OS that is lying as a backbone for all these things. So, in the last webinar, we were focusing on the SDV architecture. So this is the distributed E architecture that is currently existing in our vehicles. So we have powertrain domain, body electronics, chassis and safety, and infotainment. They're all talking to each other through a central gateway. And to this, we make a few modifications like using a HPC. HPC is nothing but a high performance computer. So we add HPCs to each of the domain, and there is a gateway that takes the central control. Okay, and each HPC will get the flexibility to scale up the features, to upgrade the existing features, and do larger computational works in minimum latencies compared to the conventional ECUs and the VCUs that we already have in our vehicles. So this is how the architectural modification has been done one step, and in future it is still going to take up furthermore lot of changes, like we will be grouping them into zonal controllers. Like what you are seeing in front of you, we'll be having the four major zonal controllers: right, left, front and back. And we'll be having the three major HPCs. One is to take care of the vehicle computational works, another one will take care of the in-vehicle infotainment, because through this only we'll get the larger interactive screen through which the user experiences can be enhanced. And the third HPC, which will be taking care of the driver assisting features. So this is how the zonal architecture has been planned along with the HPCs. And the vehicle computational unit, which is considered as the central gateway, will be connected to the will directly get connected to the cloud. So through this, over the air updates will happen. So this HPC will further communicate to the other HPCs and the exact zonal controller that needs the update as well as the upgradation. So this is how the architecture has been revised. And when you compare the role of ECUs and the HPCs in the current architecture, ECUs do the lot of computations, whereas when you replace it with the HPC, the number of ECUs will be in fact reduced. The total number of hardware ECUs deployed will be reduced. So you'll get consolidated ECUs, and the possibility for upgradation is very very high in this zonal architecture. And here the computational work will be mostly residing with the high performance computers, because comparing it to the conventional ECUs or VCUs, the HPCs will be very fast enough to do the computation, and it will take care of power saving features, and it will reduce the latency in the network, and also help in integrating AI features as well. So that is why we are switching over from the traditional architecture, domain central architecture, to the zonal architecture with HPCs integrated into it. So these were all the basic things that we were discussing during our session one webinar. And today we are going to majorly focus on this high performance computers role and the choices, how to go for it for your application, what should be the right platform that you have to abide with. And particularly for the gold box, which can be deployed as a central gateway, how you can start with the uh, G2 S3 to G274A gold box HPC. That is what is the topic of interest today. So when I was telling you that there is a big clash between the two objectives to be achieved on a single vehicle, that is, you have to retain the physical features, at the same time you have to bring the enhanced user experiences, which lies with quality terms, whereas the physical feature lies with safety terms. So when you have such clash, then the thing is, you have to learn few technologies existing and residing with the smartphone industry and the internet era. So from the smartphones and from the internet, you learn few technologies that makes them successful, and we are trying to bring it to the vehicle architecture as well. So we are going to give encapsulation, meaning abstraction between the hardware and the software. So this abstraction can be made to happen with the help of HPCs and the vehicle APIs. Okay, so this is how we are going to give abstraction, and through this we can get the two different dimensions met at a single point. So when we discuss this, we got into this service oriented architecture during the last discussion. So we had certain standards like CUVESA. In that, we specially sticked towards the vehicle signal specification, that is the VSS standard. So from the lower end, from the vehicle, if you consider, okay, the zonal controllers and all the sensors, complex sensors or the actuators, they will be talking to each other through the major network, that is CAN protocol, and the zonal controllers will be responsible for all those things. Okay, and these zonal controllers will be connected to the HPCs. Here the HPC is hidden, but you just imagine that the zonal controllers are controlled by the HPCs. So here all the communication will be in terms of signals. Okay, so you will be having your DBC to define all the signals and the messages, and at the middle level there will be an API called signal to service API, and here you have your HPC work, that is on board. Here through the virtualization platforms like hypervisors, on a single HPC you can implement two or more than two use cases, like it may be functional and a non-functional uh, thing. Okay, so you have both functional safety environment on board as well as quality management environment and on the board. So this is the middle layer is with the on board, and over that the top layer is with the cloud, it is off board totally. And here all the virtual development, testing and early user feedback analysis happens, and only after that in future the production will start, and the continuous integration and development will be uh, followed up with a DevOps plan. Okay, so this is the architecture that we streamlined during the last session. And here if you go one step ahead and see to the middleware, operating system and the hardware deployed, so at this lowest level we are all very familiar. Okay, whereas the middle layer, it is where you have your hypervisors. Okay, and the operating system you will be preferring as Linux. So this for time being you will be using it for non-functional safety use cases, whereas for safety related things you will go with the options like QNX or the default AutoSAR or the real-time operating systems. And you will be doing container based executions on the microservices. So you can see all these things. So these are the microservices. Microservices are nothing but your entire application is broken down into pieces of codes, and each microservice will represent a particular function of your application. Okay, so if you want it to be given to the user as an subscription based thing, then you can make it as a container, so that one microservice will be containerized and all the dependencies and the tools required for its runtime execution will be available in that container. So it is very easy for anyone to take it and use it, apply it on their vehicle and use it. And similarly if you see, you have the adaptive AutoSAR platform, because the no, classic platform which we are currently following will not be suitable for this scalability to go with. Hence we go with the adaptive AutoSAR platform. So this again is implemented on the HPC, and at the bottom layer you have the same things like the AutoSAR classic, real-time operating systems and all those things as usual. So we are majorly going to see the changes happening at the top layers and the middle layer. So now coming to the today's topic of interest, what is HPC and what qualifies the HPC? So HPC, as we already got introduced with, it is the high performance computer, meaning it is not a normal computer or a standard microcontrollers that we use today. It is a supercomputer with parallel processing cores in it, meaning multi-core and co-processors in it, so that it does parallel processing to save your time. Okay, and also to give scalability for the upcoming features. So without changing your vehicle, you can upgrade or do uh, future feature enhancements in the feature, so in the future. So that is what is the preferred objective of HPC. So what are the key features of HPC a high performance computer must include? It should have a massive computational power, meaning it should have multiple processors, CPUs or GPUs in it, working in parallel, so that when you get work in parallel only, you can attain the speed. Okay, that is the performance. And the second thing is the network speed, the communication speed. Compared to the normal conventional ECUs, the networking speed must be very very high in the HPCs. So they use hardware accelerators for that, and we'll come to discuss about the hardware accelerators in detail in the following slides. And the third feature that it should have is the large scale storage media, because to handle the massive amount of sensor data, like for self driving cars, you must get a larger amount of data from camera sensors, lidars, radars, and do sensor fusion and lot of calculations, and you must have enough memory space for that. So all these must be the default residing features in a HPC. So for the automotive industry, what the HPC will contribute for is for doing data analysis, complex data processing, and for doing artificial intelligence integration into it, and also advanced simulations can be done to that. So which means in the virtual cloud environment at the top layer of the SOA architecture also, you can have virtual ECUs or HPCs, where you can do early development and testing, get the user feedback, and then go for production in the second phase. So this is what is a HPC, and why traditional ECUs cannot take up the role of HPCs means because they are inefficient in handling the complex workload. Okay, they cannot be very dynamic like HPC. So you cannot go for adding a single new feature into the existing ECUs currently. That is why, because their capabilities are chosen such that it is deployed for that particular application what you meant for. So you cannot go for enhancing or scaling up any additional features into it. Okay, so they lack the centralized architecture also, which we were discussing sometimes before. And they cannot go for real time adaptability also, like for giving service orchestration or AI driven functionalities, etc. Whereas HPCs, they have higher computational powers, they have real time performance, meaning the latencies will be very low in handling the network, communication network. And
Exactly.
in short, we are consolidating the number of ECUs. So we are replacing some, for example, to roughly tell you, some 10 to 20 ECUs with a single HPC and a zonal controller combination. So it's a good thing to
Hello.
go with. So, and what
Hello.
qualifies
Savita.
a HPC? Yes.
Yeah. Can you go back to previous slide?
Yeah, I just you please excuse me so that I can take up the queries at the end,
Oh, okay. Okay.
because it will prevent me from telling what I have planned for the session. So kindly excuse me. We'll have the last 15 to 20 minutes to take up your queries. Okay. Yeah.
Okay.
So, what qualifies a HPC, high performance computer? So, how can you say that the chosen board as SOC is a HPC? So, it must have required hardware accelerators in it, meaning when we were into the first stage of graduations, we might have seen that in a CPU, to enhance its processing speed and performance, we'll be replacing a particular software loop which runs infinite times with a hardware like an adder. Okay, so likewise here, instead of CPU being engaged in a looping work, we will deploy a hardware circuitry, a special hardware circuitry for certain jobs, so that the CPU is relieved from the overload, and this hardware accelerator can do that particular job in 10 to 20 times faster than the software code that we have written. So this is the objective. So HPC, based on the architecture, whether it is having a processor in it or controller in it, we need not confuse with that, because the HPC can have either multiple processors on the core, or it can have a combination of controllers and processors. So just to start with few examples, we have HPCs provided by Intel, Qualcomm, NXP, Renesas, and Texas in the market. And if we take the NXP board of our interest, it has both controllers and processors in the same chip, in a single SoC. It has combined controllers and processors in it. We are going to just focus on this architecture in few minutes. And if you consider Nvidia or Qualcomm, they are all processor based HPCs. They doesn't have controllers in its architecture. And similarly, when you go and refer the data sheet of the HPC that you are assigned with for your project, you can come to know about its architecture, and then you can take up the right tool to program the target. Okay. And just to compare this hardware accelerator, what it is aimed to achieve, I'll just take a simple example. So if you take a conventional communication happening in your traditional ECUs, okay, it happens in the software based approach. Okay, so the protocol handling like filtering, queuing, error checking, everything will be done by the software. Okay, you will be using either interrupt pooling or DMA methods to check whether the message has been received or sent, and the processes will be involved in filtering a message, checking the errors, all those things. Okay, it is like the main CPU, it bypasses the other work and it takes care of this as well. Okay, so here the processor will be slower, it will be having the higher CPU load and less efficient in handling the traffic. Whereas if you consider a high performance computer that has hardware accelerators, so there are so many hardware accelerators. As I said, hardware accelerators are nothing but special hardware circuitries. Okay, to do an addition operation, instead of writing a C code, we can deploy an adder circuitry. Okay, so here, low latency communication engine is a special hardware circuitry that will take care of communication protocols. Okay, so here this LLCE will do the dedicated protocol working, like filtering a message, all those things what we are seeing here, queuing, error checking, all those things, so that it relieves the CPU from this hectic work, so that the CPU can focus on the major works, like making a decision and perceiving the environment, and it has to take a decision in real time, whether the vehicle has to move or stop or take left turn, or do go and consult with some other ECUs likewise. Okay, and when you deploy such hardware accelerators, what are the benefits that you enjoy? So it will be very much fast enough to process the messages. Okay, because here it will take few milliseconds to get a transmit or receive a message, whereas here it may happen in microseconds. And the CPU usage, it is excellent because it has been freed up from the regular boring works. It's not boring works, I'm sorry to use the word, but the repeated works for which it is not intended for. And it is more reliable also for safety critical communications, and it is better suited for the SDV purpose. So that is the main reason. And how does the hardware accelerator handle all this? It has separate logical blocks to do that error checking, to do the arbitration and buffer management. You have a separate hardware for this, and for filtering you have got a hardware. Okay, and inbuilt DMA support is there. And when you get multiple CAN messages, and when you wanted to process multiple messages at the same time, parallel processing unit is also there. So with these separate hardware units, you get the LLCE, which gives much faster real-time access to the data by reducing the latency. And what are all the different HPCs that you have, and how to choose the right one? So this we have already lightly discussed in the previous session, that we have the upcoming HPCs from Infineon, NXP, Texas, Qualcomm, and Nvidia. And Infineon, we will be preferring for safety and real-time applications, mainly for the cockpit development. and NXP, it acts as a gateway. Okay, gateway and a major edge processing device. Okay, so this NXP is the one what we are going to focus upon. And Jacinto boards, they are used for ADAS and infotainment applications. And Qualcomm, again, it can be used for cockpit and in-vehicle infotainment applications. And NVIDIA, it is mainly having AI hardware accelerators for processing AI, and hence it can be used for autonomous driving purpose. Okay, so this is how the various HPCs available in the market can be deployed. So we are just projecting you the various boards and their architectures here. So you can see the Qualcomm 8295 SoC. Here it is used as a cockpit controller. Okay, and you can see that it has the same SY architecture that we were focusing earlier. And here you can see the NVIDIA. So here you can have hypervisors, and the hypervisors can run a non-safety application and a safety-based application with two different operating systems. See, you have the Linux running as well as the QNX. So QNX is meant for safety-related applications, and Linux, you can have quality management based services or infotainment based applications running on this. Okay, so this is how you have to consider for which application you are going to have the implementation, and which board will be suitable for that, and what are all the hardware accelerators it is supporting. See here, if you see, you have the graphics processing unit. Okay, this will be this hardware considered, and you have direct access to imaging sensors and hardware accelerators. So image processing accelerators are here. So likewise, when you go and get to study about their architecture in their data sheets, you will get to know for which purpose it can be applied for. And here is the NXP board, and this S32G274A, it is the preferred choice that we are using. If you look at this, it has three different hardware accelerators in it. One is packet forwarding engine, the other one is the low latency communication engine, and the third one is the hardware security engine. So this hardware security, it is a special circuitry meant for cyber security applications or features. And this LLCE, it takes care of CAN, FD, LIN, and other communication protocols to be fastened up. And packet forwarding engine is a special hardware circuitry that takes care of Ethernet connectivity. Okay, and these are all the hardware accelerators that we have on the NXP board. And before going for the further discussion, I would just like to show a good demonstration on this LLC usage on the board. Jawgar, are you available?
Yeah, Kavita.
Yeah, please, over to you, Javgar. We would request you to show the demonstration.
Yeah, sure. Just give me a minute. Let me share my screen.
Yeah. So you can see normally with the software method, what is the time taken to transmit a CAN message, and with the LLCE hardware accelerator being deployed, what is the time it takes for the same message to be transmitted or received, so that we can get an idea on its real-time performance.
Is it visible?
Yes, Javgar, it is visible.
Yeah. So let me open and let me cover the device. Let me run the software. Team, as we discussed, like basically the LLC, it's a hardware that we have it in the mostly in the high performance computer to boost up the communication. So for here we have in this in the board we have different LLC. We have LLCs for uh, we can say CAN LLC for Lin Plex Ray. So different things we have. So we need to uh, uh, now currently I'm just showing about that how to do that for CAN. So in this board, we have different LLCs for specifically for CAN, LLC specifically for LIN and FlexArray. So this is basically about the communication high performance computer, and it's have the accelerator for the communication part. So let me launch the. So first I'll show you that normal routing, generally what we are doing and how much time it's taking. That is the first part I'm going to show you, team. Uh, so started. Started in main, running. I connected all my hardwares and all the things, my CAN and all the things with my hardware. So for the first part, I'm just trying to show you that. In this one, I'll just stop. I have actually two channels I connected, and I'm trying to show you that one is the routing that it is happening normally through the software, the general thing how we are doing, and one is the thing that is routing through hardware accelerator. So the first part I'm going to show you that how it is routing through normally. So I'm sending a message, can message 100 with some data. I'm sending the message and I'm getting back the second byte of the data. That is the way it is routing. It is routing in the sense it is routing through software. But here you can see that the timing 15, I mean, it's a current time, but 15, 37, 39. This is the millisecond. So it takes some millisecond, 87 to 89 millisecond. It's taking some 30 millisecond. It's taking to uh, not 30, I think 3 millisecond it is taking to process it through the software and sending back to the another controller. So there are some millisecond delay we have facing here whenever we are doing a software routing. Okay. Now I'm going to show you that how it is going to work for if we are doing a hardware. I have another message. I will show you that how it is going to work if I'm sending a to a hardware accelerator. See, it's working in the microseconds. So this is seconds, this millisecond, and it's working in the microseconds. So this is the this is the main advantage we have because see here, it's working in, it's sending in 310. This is seconds, 52 seconds, this millisecond and microsecond. So 3102, and I'm getting back in 3105. So there are some microsecond delay only it is taking if you are if you are doing a gateway. This is for basically for the gateway. This uh, hardware accelerator we are using for routing the thing. Different ECU have, as Kavita mentioned, different ECU have different accelerator for their purpose. And here we are receiving the data within millisecond. So this basically the advantage we are portraying that if you are using a high performance computer with a hardware accelerator. Yeah. So this I need to show you a demo how it is routing through a software and how it is doing in a hardware accelerator and what is the difference in that in the timing.
Sure.
Yeah. Okay.
Tell me one thing. I don't know about your hardware setup. If it is just simple one ECU, I think even simple our traditional approach will also take the very less time because of very less CPU load, right?
Sorry, I didn't get it. Can you repeat it?
I'm saying
Uh,
that simple. I mean, sending message with the latency, what you are saying.
hmm.
So that depending upon the complexity of hardware, right? So hardware setup. So what all you connected in hardware setup? Because if it is completely simple type, only one
Yeah.
ECU,
Correct,
one or
correct.
two ECU. So
So
then
what I
even
connected
traditional
is
approach will also take very less
okay.
time.
So what I connected is
Microsecond.
my ECU that is in the hardware setup. I connected my ECU with the power supply for the powering and all things, and it is taking around 12 voltage power supply. And in the same ECU, I have around 12 CAN channels, 12 CAN controllers basically. And this I mentioned that this is for the gateway we are using. And I'm trying to send a data from my bus master to one of the controller, and it is routing, taking the data from the CAN controller memory to another CAN controller where we are routing, where we need to map it, the data to the which controller. That routing, it is happening internally in the CAN controller
within
memory.
the first time. Okay, okay. So you are talking about within the single ECU. Inside that,
In the
different
single ECU,
12
the single
connectors are there.
ECU, it
Okay,
have
okay.
a
Within that,
12, 10, 10, not sorry, 15 CAN controllers we have. This for basically we are using this high performance computer for gateway. So it have 15 CAN controllers, and I didn't remember how much lin controller and flex ray controller we have. But here I am just show that CAN controller configure, CAN controller routing and all things, but it's for the gateway. So here we have different type of CAN controller. Basically the accelerator, they will give it for communication part, CAN, flex ray, ethernet and all the things. And if you are choosing
within,
different controller, different microcontroller, different HPCs, they have their own accelerator. Like Kavita mentioned about that Qualcomm and Nvidia, they will have some high performance computer, not for maybe the communication, they will do for processing their videography and all the things, that video capturing algorithm and all things. So what all the performance they need to do for the video capturing processing algorithm.
yeah,
Here we have only one controller with the different one ECU with the different CAN controllers in that.
okay, okay. Single ECU in that different connectors.
Yeah.
But what I know, like within the chip, we communicate via I2C communication. So, what
Sorry,
protocol
did
you
you?
Okay,
I2C?
HPC
I'm
can
sorry to interrupt Abhinav and Javagar. I hope if you have any personal doubts, you can just mail us so that we can reach you out.
Okay, okay, yeah,
We
sure.
have minimum time left off to complete the other things.
Oh, okay, okay.
So like we are
Anyway,
using
thank you.
CAN, we have different CAN controllers, and with that CAN controllers, we are routing the data. So that is the
Okay.
solution. I just need to give it. Yeah. Yeah, Kavita, I'm hand overing to you. So if you have
Okay,
any
thank you so
doubts or
much,
something, you
Yoga,
can
for
just
joining
mail
us
it
for
to
the.
me. So
Yeah.
yeah, thank you. Thank you, team.
So now it's time to explore more on the features of the gold box, that is S32G274A. And as I was already telling you, it is a high performance computer. It is an automotive grade performer. Okay. And if you look at the processing power, see, this is the S32G2 board. We call it as gold box. And you can see the S32G2 processor here. So see, this is the single SoC that has multiple processing cores in it. It has got three M7 cores controllers and four A53 cores in it. So if you just look at this architecture from the data sheet only, I have taken this. So you can have the three ARM Cortex M7 cores and the four A53 cores. So A53, it is the processors. Okay. So you have totally seven different cores packed on a single on chip, like mentioned as S32G274A, and it has all other features like for memory and storage. It has got see the dynamic data RAM, so it can also act as low power data RAM. And it has got 512 KB SRAM, and external storage supports like eMMC, SD card, etc. And for networking and connectivity, it has got fantastic Ethernet interface, like along with the TSN, time sensitive network. So that is how this is particularly chosen as a gateway controller, because it can have the fastest means to communicate the message in real time. And it also supports so many networking protocols like CAN, CANFD, LIN, FluxRay. You can just see it from the architecture. And it has normal serial communications, USB, UART, SPI to C interfaces as well. and to enhance the security features, because when we speak about SDV, security is a major concern. So we have a separate hardware accelerator for security purpose, that is the HSE, hardware security engine. So these are all the different features available on this core architecture. So you can see, this was the thing I was speaking about. You have so many memory features enhanced. For safety, you have separate hardware accelerator, and you have the network accelerator like LLCE, and for Ethernet you have PFE here. Okay, and you have the cores, that is Cortex M7 cores and the A53 cores in it. So this is how it has been architecturized. And if you look at the service oriented architecture, see, over these hardware accelerators you can have a virtual environment, that is a hypervisor, and the hypervisor can run a safety and a non-safety application in parallel on the same A53 core. See, this is the hardware that we were talking. You have 4 A53 cores and 3 M7 cores. On a single A53, you can deploy a hypervisor, and over the hypervisor, you can have safety and non-safety parallel running on it, because they are perfectly isolated. And if A53 wants to communicate with M7, or vice versa, M7 wants to communicate with A53, you can use the interprocessor communication framework. We call it as IPCF. So through this technique only, the multi-core communication is made to happen. And see, this is one of the use case that ANSYT team has developed as a proof of concept. And this is a simple parking assist use case. And here, if you see, M7 will be getting the ultrasonic sensor inputs through GPIO, and this will be written in the shared memory, and it will rise an interrupt provoking A53 from the low power mode. So A53 will go and read the ultrasonic sensor value. If there is an obstacle detected, A53 will be like a client, it will request the Raspberry Pi with the some IP communication for the vision data, the camera data, processed camera data. So the Raspberry Pi acting as a server, it will return either the detected object is a man, machine, or something else. Based on that, the A53 will be able to make decisions on processing it, and it will send the control signals to the zonal controllers or to the actuators, whatever necessary it has to do. And this A53, if you look at this, it is connected to the cloud environment, and through this only it is able to get over the air updates for new features. And from A53, it can share to the other HPCs or to the same microcontrollers or zonal controllers wherever it is necessary and applicable. So this is a use case that we have implemented and tested on the board. And this is the process that we have run. As this is what I was explaining. So M7 will detect the obstacle, and it will intimate A53 to confirm whether it is a obstacle to take control actions on the brake or not. Based on the vision data from the Raspberry Pi through some IP communication, the control action will be taken by A53 if needed. And inside this, between A53 and M7, as I already mentioned, IPCF is the framework to do multi-core communication. So this is shown you as demonstration. Now I request Anish to take up to show the demonstration between the multiple cores A53 and M7, how it is talking to each other. Anish, are you available?
Yes, ma'am.
Yeah, please.
Ma'am, I couldn't share the screen.
Now you can do, Anish.
Okay. Can you see the screen?
Yes, Anish, it is visible.
Okay. So we have this M7 microcontroller and A53 processor. So in order to work with IPCF, we have built an M7 application, IPCF sample application. And for A53 processor, we need a custom Linux and also IPCF drivers. Okay. So we have built the all this application and build our Linux and flash into the SD card. So everything is set up. Okay, I'm going to launch the PicoCom, which is a serial terminal.
So we program the A53 process through the Linux machine as host device, and for M7, we'll be programming it through the bare metal codes from S32 Design Studio, being a controller.
So at the boot, we have to interact with any keystroke in order to flash our M7 binary, M7 IPCF binary to to the M7. So through U-boot, we are using U-boot. First, I am turning off the cache to prevent caching issues. Next, clearing a memory space in SRAM, which is the RAM the M7 has access. Then I am loading our, this is the binary, M7 binary, IPCF binary. So I am copying this from SD card to DDR4 RAM. From DDR4 to our SRAM where M7 has access. Then I'm starting that memory region application. I'm booting the system to Linux. So we have loaded this IPCF binary to M7, and now we are booting to Linux. So these two are our drivers. This is for inter-process communication. Like we are enabling to enable the shared memory. This is the application driver, sample application. So I am going to insert this shared memory driver. Then sample application kernel module.
So to the monolithic kernel, Anish is adding the loadable modules, the driver modules required for IPCF.
It's dynamically added. Okay, so you can see this. These two are working together to make our IPCF work. Now, like clearing the kernel logs. Now, with this message, I am sending this one to our M7 core, like from A53 to M7. We have sent this message. Now, we can see this. We are starting around instance 0. Instance 0 sending message 1 and also a message hello world from kernel. So this kernel means A53 core, and replied message 1 hello world from core 4 means M7. So here with this we can prove that this communication is established.
Yeah, we have just demonstrated you with a simple hello world use case. Whatever may be the sensor data required to be transmitted or control messages need to be transmitted between the multiple cores, you can make use of the same approach. Thank you, Anish. Thank you so much for the demonstration. Yeah. So this was the idea that we have shown you as demonstration. M7 core, it is able to talk to A53, and A53 is able to acknowledge or talk back to M7 core. So this how it is made means A53 we are programming through the Linux host machine, and M7 we are programming this. The binary file is flashed into it from the S32 Design Studio. From the SD card through the respective communication channels, we are making the booting to happen through the U-boot bootloader, and the application is run successfully on this S32G274A. So this was the demonstration that has been narrated to you, and we have also implemented the suspend to RAM concept to save the power when the core is not being used. When A53 is not in use, we have to keep up the power. So that is also a main requirement in SDV. So that we are doing with the help of suspend to RAM technique. And we have also containerized this ultrasonic sensor part to show you that the microservices containerization has been done successfully on the same platform. And we have also implemented Zen hypervisor over the A53 core to run both safety and non-safety applications parallelly on the same core. So this brings the essential usage of this HPCs here. And we are also doing proof of concepts on adaptive autoserve projects, some IP projects, and containerizing multiple microservices parallelly. So I'll end it here. If you have any queries, you can ask me.
With what I was saying, when you were saying that HPCC is making centralized architecture, but before
Yes.
that also we saw the gateway was in the middle, so it was also somewhat central, like all
Okay.
the what to say, all the local network. I mean, not local. Okay, all the sub network was
Okay.
interacting through gateway only, right?
Okay.
So that was
So
also
your doubt
centralized
is in
architecture
the
also.
traditional architecture also we had the gateway. Now also we have the gateway. Then what is the difference, right?
And it's adding the HPC means more
Yeah. Yeah. So
devices
now when
increasing.
you make a HPC to act as a gateway controller, okay, compared to the traditional gateway, this will further increase the communication speed. So that is what you saw from the demonstration of Javagar, right?
Mm.
So it will be in real time, it will be very fast, and the latency will be further cut down. And the other major thing is scalability. So this gateway controller can communicate with the cloud, and it can fast forward the updates to the other HPCs and to the respective zonal controllers in a very fast, effective way. I
So the
hope now you
faster
get
way
this.
is Ethernet only.
Yeah.
Okay. Are we
Kavita,
using KWP?
Yes.
uh, sorry, Abhinav. You were
Okay.
speaking something. I interrupted in between. Yeah, please continue.
No, I'm saying if a network having KWP and CAN and LIN protocols, so how that is interacting with HPC?
Yeah, HPC can handle all those things as well. How the traditional architecture handles those things, all
Yeah.
those features can be retained. Along with that, you can have these additional things like one is complex processing, edge processing can be done, and the network speed can be fastened up using this LLCE and the PFE hardware accelerators. The traditional features that is currently there will be retained as such without any modifications. That is sure.
This hardware accelerator you were seeing, that was part of CPU like ALU, or it is separate from CPU. These all those hardware architectures we showed.
Yeah, hardware accelerators will be
Not
under the control of the CPU only, definitely.
as ALU, as part of ALU.
Not like ALU. ALU is one specific portion of the CPU, right?
Yeah.
Hardware accelerators are special hardware circuitries that comes along with the system on chip. Along with the
Oh,
A53 core, this hardware accelerators also come as additional hardware circuitry.
okay.
Is it
Kavita, I
clear?
have one
Yeah,
question.
go ahead.
So basically, when do we call a system as HPC? So are there any guidelines or any specific definition? So when you explained briefly, like if that is having hardware accelerator, that is one part. So
Yes.
similarly, like, do we have other guidelines? After that, we used to call a system as HPC.
Yes, hi, yes, Vaibhav. When you go for selecting a HPC, the
Hmm.
two major things that you have to consider is compared to the traditional ECUs, it must have some additional built-in hardwares to take care of the computational tasks and to take care of the scalability works.
Okay. No, that is fine. But what I am asking is like,
Mm.
what is the thing that makes a system as HPC? Is it based on some configurations on or the what processor you are choosing? What is that?
Yeah, you should have the multiple cores that acts as parallel computing units.
That is there in normal standard
Yeah, along with that,
computers
you
also,
must
right?
have hardware accelerators to support certain features. Like if you consider automotive network, then you should have facilities. Normal apart from the normal Ethernet, PFE is an added hardware accelerator. Likewise, when you take NVIDIA, you do have hardware accelerators for image processing. So those things qualifies it as a HPC.
So based on certain variants of processor, we used to call as HPC.
Yeah, when a normal performing computer can give you a feature, the HPC can have some additional hardware circuits to make it much more happen in a much more faster way. And for even security and to handle cryptographic things, it has got a separate hardware circuitry. That is why we call this G2 as a HPC. And if you go for Qualcomm and other things, for infotainment purpose, it may have certain hardware accelerators that makes it to be called as a HPC.
So when we are saying HPC, that is part of a single SoC, right?
Yeah,
Everything.
yeah.
Okay. Okay. Understood. Understood.
Yes, yes. Any other queries, or shall we stop here? Okay, if you have any additional queries or if you wanted to get any detailed informations, you can contact our team info@answerconsulting.com. Thank you so much for your participation.
Also, if you are looking for
Yeah.
any corporate trainings or consultation on SDV, please write to us. Our email ID is info@answerconsulting.com. Just pasting on this. Thank you, team. Thank you,
Yeah.
Kavita, for
Yeah.
the wonderful delivery. Thanks all. We will meet on next month again.
Yeah.
Bye.
Thank you, team. Bye bye.
Thank you. Yeah, thank you all. Bye.
Thank you all.